Let's take a look at question 11 in topic set 7. This is a combination question of the photoelectric effect and the Bohr model of the atom, the one electron atom or ion. And in this case, it says, what's the kinetic energy of an electron that's ionized from a lithium ion, lithium 3 plus ion in this case, using a photon of frequency 5 times 10 to the 16. I know this is a photoelectric situation because it says that the electron is ionized using a photon. So in other words, you have metal surface where you have electrons attached to this lithium 3 plus ion, and the surface of the metal is hit by light with a certain frequency, and that light manages to knock out the electron such that when the electron is knocked out, it has some kinetic energy, it has some speed, and it's moving at a given kinetic energy. So we can calculate that kinetic energy if we remember this relationship in the photoelectric effect, which is that the kinetic energy of the electron will depend on how much energy the photon that hits it originally has, minus something we call the work function. And the work function, if you remember, is just the energy that holds the electron in the atom, or in this case in the ion. Okay. All right. So how do we calculate the kinetic energy? Well, obviously we're going to need to find the work function right here, right? Because we already know the energy of the photon, or at least we can calculate it because we know the frequency. What is the work function? Well, the work function is the energy that holds the electron in the lithium ion in this case, but could be calculated using Bohr's model of the one electron system, right? Because in the Bohr model, the delta E is the energy transition from two different orbits in an atom or an ion. So in this case, we have our +3 lithium nucleus, and then we have these orbits that the electrons could be located in. And in this case, we want to knock it out completely. So we want to start from the ground state, which is n equals 1, and we want to pull it out all the way. So what is the orbit number when the electron is completely out? Well, that means that the final value of your n must be infinity. Now, remember in the Bohr model, we have this equation, negative RH. This is a one electron system. So we have this z squared, which is equal to just the number of protons squared, or the atomic number squared, and then 1 over n final squared minus 1 over n initial squared. And this energy is really exactly the same energy as the work function in this case, which is the energy that's holding that electron together. Okay, so we can calculate the work function, in other words, by calculating delta E. Once we have that, we subtract it from the energy of photon to get the kinetic energy. So let's do that step by step. We're going to first calculate delta E, and the Rydberg constant, or RH, is 2.178 times 10 to the minus 18 joules. The atomic number, the Z for lithium, is 3, so we would do 3 squared in this case. And then 1 over n final. N final is infinity, so we're going to do infinity squared minus 1 over the initial n, and that is at the lowest level, so that's 1 squared. And this calculation right here would just give you 0, and this is of course just 1. And you have a -1, a negative here, so the negative and the negative ends up canceling, so you get a positive number. So that makes sense because you need energy to knock this out. And so when you calculate all that out, you would get 1.96 times 10 to the minus 17 joules. And that's your work function. So then now we bring it back to the original equation, which is this one right here, to calculate the kinetic energy. So the kinetic energy is going to be the energy of the incoming photon, which is h nu, minus the work function, that's your h, and then the frequency is 5 times 10 to the 16 per second. Subtract that with the work function of 1.96 times 10 to the minus 17 joules, and what we end up getting is 1.35 times 10 to the minus 17 joules.